Good. So let's recap quickly what we said last. So if you have a norm in your vector space, then that also always gives you a metric given by this rule. Distance of two elements equals the norm of the difference. Difference can always be computed because you are in a vector space. But then you also have things like convergence. Remember, for the notion of convergence, we said something like distance of xn to x goes to 0. Okay, and now instead of that distance, we can say the norm of xn minus x goes to 0, right? And for Cauchy sequences, we would say instead of distance of xm and xn goes to 0, we would say that norm of xm minus xn goes to 0 as m and n go to infinity. Okay, so we can do all of these things, and one of them is what we're going to follow now, which is completeness. Okay. Remember, completeness is, so your space is complete if every Cauchy sequence even converges and has a limit inside the space. That's going to lead us to the next definition. Section 2.3, Banach spaces. Definition. A normed space x together with addition alpha times and the norm that is complete. It's not the word we're going to define. With respect to the metric D that is induced by our norm is called a Banach space. That's the new word. Banach spaces are named after Stefan Banach, probably the greatest mathematician in functional analysis of the last century. He lived from 1892 till 1945, and that's what he looked like. I hope during the next few hours you will get an idea, a feeling for why completeness is such a crucial property and why normed spaces that are complete deserve their own name. Let us start with an example. So a first example is the space of real numbers together with the usual norm. So the norm of a real number is just its absolute value, which is its distance to the point 0, which makes R one of the simplest normed spaces that we've been discussing. And for it to be a Banach space, it only remains to show its completeness. And I said this before, so the completeness of R is in fact part of the definition of the real numbers, and it's this part that makes the definition of the real numbers so tough. So the completeness is given by definition of R. So this is a Banach space. Okay, we didn't have to show anything really here, but still, I think it's the first example that should be discussed. Let's look at the next example. Let's take R2. Okay, we take the usual norm in R2, the Euclidean norm, let's say. So the norm of a vector x1, x2 is just the 2 norm, so it is the root of modulus x1 squared plus modulus x2 squared. Again, we could drop the modulus signs here. I'm just getting used to this because we use it for the p norm and for complex numbers. Again, we know it from the previous section that this is a normed space, and it only remains to show completeness. Completeness, question mark. Well, this time we have something to do. So by the definition of completeness, you take a sequence, a Cauchy sequence in that space. So let xn n equals 1 to infinity be an arbitrary Cauchy sequence in R2. That means all the points x1, x2, and so on are in R2. And let's put the notation as follows. So let me write xn as okay, the top component shall be denoted by a top 1 and the bottom component by 2 at the top. And we are putting the index at the top in brackets so nobody will confuse them with exponents, with powers. Okay, so they are all in R2, so each of these entries here is just a real number. Okay, and this is a Cauchy sequence. To be shown, it converges. Okay, so the sequence xn converges in R2 with the corresponding norm as above. So I'm afraid we have to write that down, what Cauchy sequence means. So for every epsilon greater than 0, there exists an n null in the naturals, so that for all m and n greater than or equal to that and 0, we have the norm of xm minus xn less than epsilon. Okay, so what's the norm? Well, it's defined up there. It means okay, so let's just quickly recall this vector here is the norm of xm with a 1 here and xm with a 2 here, and we subtract that vector xn with a 1 here and xn with a 2 here. Okay, so obviously you can subtract component wise, and then you would get the following. So you get that the root of xm1 minus xn1 squared plus xm2 minus xn2 squared is less than epsilon. Okay, now clearly you can just ignore the root and put a square here. And then you could imply, you could conclude that xm1 minus xn1 squared is less than epsilon squared, and also the second term, xm squared minus, not squared, 2 minus xn2 squared is less than epsilon squared. Now we can drop the squares, drop this and this and this and this. And if you read from the top until here and here, you get that the sequence of all first components and the sequence of all second components are Cauchy sequences in R, right? But here's the clue. Now R is complete. This was our first example. So we know that they both converge, right? So we know that there exist limits. Let's call them just x up 1 and x up 2 in the real numbers, so that this one converges to this and this one converges to that as n goes to infinity. Okay, and I think you can see what we're doing here. So starting from a Cauchy sequence of vectors, we've gone down to a Cauchy sequence of coordinates for each single component of the vector, which are now real valued. But because the reals are complete, they all converge. So for every component, we have a limit, and now we just put them together, and that should give us a limit for the sequence of vectors. That's how the story goes. We just have to get the maths right. So now let's show that our vectors xn, which are just xn top 1, xn top 2, converge to this vector x top 1, x top 2, which we might denote by just x. Okay, what does it mean to converge? Here we have to write down the distance of the two, xn and x. That is by definition just the norm of xn minus x, which is just the norm of xn1, xn2 minus x1, x2. And that can be spelled out by the definition of our norm as the root of first component squared plus second component squared. And we have to show that this goes to 0 as n goes to infinity. There are more than one way to see this. The probably easiest is to just use this convergence here and say, okay, therefore this goes to 0, and then that convergence here, and say, okay, that's why that goes to 0, and hence the whole thing goes to 0 as n goes to infinity. But let me also show you the other argument that we could have used in the last line, because we will need that for other examples. What you do is you go backwards a little bit and again read these lines, and then you say, okay, if this holds for every sufficiently large m and n, then you could as well send your m to infinity and then replace in this expression xm1 and xm2 by just the limits x1 and x2, and you would end up with pretty much what you see down here. Okay, and then you could conclude that this is less than epsilon squared, or if you take the root less than epsilon, and there you are. Okay, that way you immediately see convergence too. Because this technique is the mother of all proofs of completeness, let's quickly recap the essence of that proof again. So what did we do? We started with a sequence, a Cauchy sequence of vectors. Let me try to get that right here. Okay. And so on, and that was a Cauchy sequence in R2. By writing down what it means to be a Cauchy sequence and by evaluating the norm expression, we could see that this sequence of real numbers as well as that sequence of real numbers both are Cauchy sequences. So this is Cauchy in R, and this is Cauchy in R. Now using completeness of R, okay, complete this R and this R, you could conclude that this converges to a limit, let's call it x1, and that converges to a limit, let's call it x2, and by just gluing these two limits one on top of the other, we get our vector, which turns out to be, and can be easily shown to be, indeed the limit of this originally Cauchy sequence in R2. Now this is clearly in R2 because you get it by just taking the limits, which are real numbers, on top of each other, and the fact that this is convergence is easily checked, like we did in the last 3 lines of the previous proof.